Okay, so we're going to go ahead and take a look at problem number 9 and a couple other little things here. So anyway, guys. What, Dean? Okay, so we've got, yes, what's up? Is there homework due? Well, I mean, we have some things that we should be turning in tomorrow because the test is there. And so I probably during the period today will like map out what that would be. So figure out what we got here. So we got water that's flowing in at 18 cubic feet per minute. That is what piece of data is being described by this right there. That's dV dt. Okay, so the problem is handing me dV dt is 18 cubic feet per minute. Okay, and you can kind of tell that volume is cubic feet, time is minutes. That kind of makes sense. Into a conical tank with a radius of 12 feet and a height of 7 feet. So we've got this kind of look right here. We've got a radius of 12 feet and a height of 7 feet, like this. And one of the things that we've actually talked about is that means that at any given moment, as water kind of comes up this thing right here, what is the ratio of then the radius to the height every single time? It has to be 12 over 7. The radius and the height have to be in a constant ratio of 12 over 7. Well, that gives us a couple of things that are very, very helpful. One of those things is that it actually mentions the height, so I'd like to actually get rid of the radius if I can. So I know that the radius is 12 over 7h if I did a little cross multiply, right? So what's nice about that is we could actually say then that dr dt, I'll just write it right up here, dr dt is 12 over 7 dh dt. So in this particular problem, it asks what dh dt is, but the kind of the cool thing is if I had dh dt, I could just multiply by 12/7 and get dr dt. They just kind of go hand in hand that way. So what's the volume of a cone? You guys remember what the volume of a cone is? 1/3 pi r squared h. That's our story. It's 1/3 pi r squared h. So one thing that's an interesting deal, and I don't know if you guys know this, I'm going to set this off to the side. Let's imagine that you had a pentagonal pyramid. You guys know what the volume of that shape is going to be? 1/3 base times height. You have a cone. It's 1/3 base times height. Anytime it is pointy, 1/3 base times height. And you might right now be like, why is that 1/3 base times height? Calculus. Next semester, we're going to go and we're going to take it 3D, and you're going to actually find out where all of those things come from, and you'll actually be able to justify why that's the case. Up till now, you just had to take somebody's word for it, but we're going to actually derive that formula and find out why it actually works. So in this story right here, I know the radius is 12 over 7h. No. Sorry. It's been vacation. I didn't turn my phone off. Okay, there's that. Okay, so 12 over 7h, quantity squared, h, and so that's a lot of stuff, isn't it? So I've got 144 pi h cubed over, what's 49 times 3? Is that 147? I think so. So that's the volume related directly to h. So what we could do then is when we take that derivative, that would be dv dt, right? So I've got dv dt is equal to all of this stuff right here in front is a constant, so remember it doesn't really do anything. What's the derivative of h cubed? 3h squared dh dt. Now, if you go through the data that you were handed, it says, what did they give me in all of that data up above? Did they give me dv dt? It's right here, it's 18. 18 feet cubed per minute. All of this stuff is a big fat constant. They said when the thing is 5 feet high, so that's going to be 3 times 5 squared. And then last but not least, dh dt, and that is exactly the thing that we wanted to find out, right? So that looks like we're pretty much done with everything except for basic math, right? We just have to do a little bit of division and we're good to go. Alana, you want to come grab yours, and Mariana? There's one for you as well. Okay. Is that good enough, Amber? I didn't show you the very last step of dividing it, but that's pretty much it. All right, anybody else have any questions? It's been a little bit, hasn't it? Okay, so anything that you guys need to talk about before we do a little teeny bit of forward motion, new material? All right, well, then we're going to do a little something new. And this is called the mean value theorem, everybody. The mean value theorem. Yes, yes. On the test? No. I don't think so. No, then no. Okay. No, and in fact, I don't think I would collect that at the test anyway. I think I'll probably wait on that one. Okay, so here's the deal. The mean value theorem is really like kind of a complicated thing to lay out, and yet it's pretty simple pictorially. So let's imagine you have a continuous and differentiable curve. Now, if something is ever continuous and differentiable, the magic word that everybody uses is smooth, right? What makes something not be continuous and differentiable? What would make it violate that? If there's a hole in it, then it's not continuous. Yep. If there's a vertical asymptote in it, that's not continuous. If there's a cusp, it would not be differentiable. All of those kind of things, right? So as long as it's a nice, simple, smooth curve, you know, it goes like this, and we have some interval A here, B over here, and I played connect the dots with this thing right here. So I'm going to give you a picture of it first. So this is a secant to the curve. You guys with me on that? This is a secant to the curve. We've used the word tangent a lot in here. A tangent hits a curve in precisely one place in that particular neighborhood, right? But if you could find this, have you found the slope of the curve? Going back to earlier days, Gianni used the nice little joke about calling this mean. He used the word average, but didn't we talk about average rate of change in here a while ago? A-rock? So if I were to find that line, wouldn't that line be the average slope over that interval? Well, here's the deal. If we have that secant on the interval AB, and it is a smooth, nice, continuous differentiable curve, then the mean value theorem simply says that somewhere this curve will have precisely that slope. Does that make sense? So if this slope from here to here is 5, then somewhere on here that slope is going to be the same. And on this one you could tell that it would happen 2 times. Once is right there, and once is right there, because what do you see about the places that I chose to draw that? What do you see about those slopes right there? They're kind of parallel to the given one that we have, aren't they? Kind of makes sense. So that's all the mean value theorem says, is that if you take a look at the secant to the curve, somewhere the curve on that interval has to match. So here we go. This is the theorem. If f of x is a continuous differentiable function on closed interval AB, then, so all of that was just to say that it was a nice smooth curve, no holes, no cusps, no vertical asymptotes. So it's some continuous differentiable function on some closed interval AB. Actually, I probably should use capital A and capital B since I did that in the picture. So cap A, cap B. Then, here's where it gets a little bit weird. So at math, we sometimes have abbreviations for things. So this symbol right here says there exists. You ever see a capital that just means there is some place? So notice that what I'm referring to is these two yellow lines right here. There exists at least one C. I should write that underneath so you can see a little bit better. C that is an element of AB. So there's some value in between A and B. C is some element of that set A to B, such that if you did f of B minus f of A over B minus A, now what does that look like to you guys? What is f of B minus f of A over B minus A? That's your A-rock value. That's this line right here is f prime of C. There is some place where the slope of the tangent matches the slope of that secant. It's a pretty simple little idea, okay? So like I said, it looks kind of big and meaty, but it's a fairly simple concept, and I just wanted to look at a couple of very, very easy ones. So let's just imagine we had f of x is x squared minus 2. And I had a nice little interval of -1, 4. So what we want to do is I want to find out what is that value that is guaranteed by the mean value theorem. Now, pictorially, we don't, and in fact, we don't have to have a picture, but sometimes a picture is nice. You know, x squared minus 2 is going to look something like this, right? So what is f of -1? Isn't, if I plug in -1, don't I get -1? Okay, -1, -1. If I plug in 4 up here somewhere, 4 would give me what, 14? 16 minus 2? Cool? So here's what it says, that if we look at this graph right here, now keep in mind, I'm not really taking great pains to make this perfectly to scale or anything like that. But what is the slope of this line right here? What is f of B minus f of A over B minus A? What is f of 4 minus f of -1 over 4 minus -1? Yeah, that's the whole answer. Yeah, this was 15, right? And so the total answer was 3. Everybody cool with that? So what the mean value theorem says is somewhere the slope of this curve will be identically 3. How would I figure that out? Well, I've given you a hint. The answer to every question in this class is the derivative. What does a derivative tell you? The slope. So I want to take the derivative. Here's f prime of x, right? It has to be the same as the slope of that secant. So where would that happen? When x is at 3/2. So somewhere over here on the curve at 3/2, by the way, what is 3/2 squared? That's 9/4, right? 9/4 minus 8/4 is 1/4. So at 3/4, 3/2, comma 1/4. So C is 3/2. So F prime of 3/2 is equal to 3. Do you guys follow me on that one? That's the place where if you graph them, they would actually be perfect. What do you think? Is that pretty simple? Not too shabby, not too hard. Okay, so I do think we should probably look at one such problem here. No, because at -3/2 wasn't the slope coming down? Yeah, so there is some symmetry in there, but not quite. So for my other question, because I really only wanted to look at two of them, I have some function f of x is, let's see, g of x is x cubed minus 4x squared minus x plus 1. Here's g of x. I've got an interval from -2 to 4. And I want to find the value guaranteed by the MVT. Now, I got to say, when I was in your shoes, I did not like this thing because doesn't mean value theorem and intermediate value theorem and average value theorem all sound the same? Yeah. By the way, those are all totally different things. The intermediate value theorem just said, hey, if you go from here to here, it had to go through every single thing on the way. The mean value theorem, we just talked about it, but the average value, oh, that sucks. That's totally different. Doesn't that seem strange? Because you've always been taught that a mean and average are the same thing. Yeah, so we're going to actually just have to be careful about the way that we play with that. So let's use our calculators, everybody, because this problem was not designed to be kind. It just wasn't. Okay, so let's go ahead and remember how we can efficiently use our little machines here. I started that first problem in a nice place, but I wanted to kind of just show us one where it might not be so nice, but we can get our answers pretty quickly. So what's the first thing I'm wanting to do is I want to find out the value that is guaranteed by that mean value theorem. So how am I going to figure that out? Let's do vars. Y var is y1 of what? Of 4. Let's find out what is y1 of 4. So when I did this one, I got -3. I'm supposed to subtract the value when I plug in -2. And I got -21 all over 4 minus -2, which is 6. So it looks to me like I got -3 plus 18 over 6, or that's 15/6, which is divisible, so 5/2, right? What do you guys think so far? Did I make a mistake there? I did make a mistake, didn't I? Oh, I see what I did wrong. I actually already got the answer 18 right here. I actually already put them together and got 18. I just wasn't thinking. So it's number 3, isn't it? Okay, so what are we doing for the last portion of the question? I know what I want the slope to be 3, right? So set the derivative equal to 3. But in this particular case, my derivative is not quite so nice. So what do you think we should do, considering I'm basically giving you a big fat hint that this is calculator active? What are we going to do? Let's go with our quadratic formula, and we are sanctioned laziness right here because we have a program right here that is our little program quad. And we had values of 3, -8, and -4. Now, one thing that's important is the mean value theorem only talks about things whose answers are in the interval from -2 to 4. So I'm going to ignore anything outside that interval. So, which ones count? Looks like they both count, don't they? They both are inside the interval from -2 to 4. So the value guaranteed by the mean value theorem would be at -0.431. and x equals 3.097. And in those cases, those are the values that would be guaranteed by the MVT. So is mean value theorem particularly hard? Pretty simple, isn't it? Not too shabby. So there's some sneaky little ways that on some tests we can do some fun things with those, but we'll talk about that later. In other words, well, I'm just going to leave that be. But one of the reasons why that's important is, what if I have a slope of 0 somewhere, and another one, what if I have 2 points that have a slope of 0? So what would be the average rate of change between those two values if from A to B the slope is 0? Then its slope would be 0. So would the mean value theorem guarantee then somewhere on that interval it will also have a slope of 0 as well, at least one place? So if that happens and the two values somehow are horizontal to each other, it's going to guarantee that somewhere there's going to be a max or min in that interval. And keep in mind, I can call it a max or min because I said it was smooth and continuous, right? So I guaranteed that we didn't have any cusps or anything like that in that region. So I think that's a pretty simple, was that rough? Pretty simple little idea to say, hey, find your average and then set it equal to your derivative and solve. That's the mean value theorem. That's all I wanted to present today to you guys. So the rest of the period, what my intent was, is to have you guys kind of go through the review, kind of reacclimate to the world of calculus a little bit, ask for some help. Do you guys, would you guys want to go over any related rates or any like topic like logarithmic differentiation? Anybody need to talk about chain rule? Any of the above? Or do you just kind of want to start going over your review and thinking about stuff? All right, so we're good.